topic is dimensional homogeneity. There's a basic principle that states that the equation must be dimensionally homogeneous. It means that every term in an equation must have the same net unit of dimensions or net units to be able to add, subtract, or equate them. In dimensional homogeneity, there will be the introduction of the gravitational constant, or more commonly known as the G sub c. G sub c has both for SI units and British unit. For SI, it has 1 kilogram meter per Newton second squared. And for the British unit, we have 32.174 pound mass, foot, and every pound force second squared. Through the dimensional homogeneity, we can modify the simple formula for kinetic energy and potential energy. For kinetic energy as originally as 1/2 mv squared into mv squared all over 2g sub c. And for the original mgh for potential energy, we're going to have mgh all over g sub c. For the preceding examples, we will discuss the application of G sub c for the kinetic energy and potential energy, as well as the proving if both equations are dimensionally homogeneous.
Upon discussing what dimensional homogeneity is, let's have some basic examples. Here we have is the kinetic energy given by the formula 1/2 mass times velocity squared, wherein the resulting unit would be joule, which is equals to Newton meter. In testing if an equation is dimensional homogeneous, let's put the desired unit on the left side and the formula on the other side. Plotting the units, we have 1/2 mass in terms of kilogram, velocity in terms for meter per second. And solving it, we get 1/2 kilogram times meter squared all over second squared. As we can notice, the left side and the right side is not dimensional homogeneous. And because of this, we're going to introduce the gravitational constant, which is equal to 1 kilogram meter per Newton second squared in SI units and 32 pound mass feet per pound force second squared in English units. In our case, we will be using the SI units, which is 1 kilogram meter per Newton second squared. And plotting it into our formula, we get 1/2 times kilogram meter squared per second squared all over 1 kilogram meter per Newton second squared. And cancelling the units, we will be arriving at 1/2 Newton meter. Disregarding the constants, we will be having Newton meter is equals to Newton meter, which makes the equation dimensional homogeneous.
X and A should have the same unit because x squared over a squared should be dimensionless because of the quantity 1. So, by assuming x and A have the same units, we can cancel these and these. And the equation will yield 1 over x in the left side while on the right side will yield x squared by disregarding 2. As you can see, the equation is not dimensionally consistent.
Here is another example of a not dimensionally consistent. In equation of fluid pressure, pressure is equal to the density times the gravity times its height. Now, we all knew that the pressure unit is Newton per meter squared. Now, as you can see in this equation, in the left side unit is not consistent to the right side unit. So, we will now introduce the G sub c factor, which is 1 kilogram meter over Newton times second squared. So introducing that G sub c factor, we can now cancel the remaining units to get Newton per meter squared.
there's one more example of not dimensionally consistent equation. The potential energy is equals to mass times the gravitational force times the height. And we know that the potential energy's unit is Newton times meter, and the other unit is in kilogram meter per second squared times meter. So this equation is not homogeneously consistent. So we introduce the G sub C, where it is in kilogram times meter per Newton times second squared. And we divide it in the equation. So we got we cancel this, and the remaining unit is Newton meter.
Hello everyone, we have to talk about the dimensional homogeneity. So, what is dimensional homogeneous equation? For example, we have the total velocity, which is equal to velocity of 1 times velocity 2, then the other velocity, which is b sub n, and then we should have the unit of meter per second is equal to meter per second plus meter per second, then so on and so forth. So if we simplify that, meter per second will be also equal to meter per second, which is dimensionally homogeneous. And then let's have another example. We have the force, which is equal to mass times the gravitational acceleration. So if we have the units for that, we have Newton, which is equal to kilogram meter per second squared, which is not dimensionally homogeneous, because although we do believe that kilogram meter per second squared will be equal to Newton, but in engineering we do not believe in that. So we define another variable, which is what we call the G sub C, which is equal to 1 kilogram meter per Newton second squared, which is also equal to 1 gram centimeter per dyne second squared, which is also equal to 32.174 pounds mass feet per pound force second squared. So if we have to make it dimensionally homogeneous, so we have the formula mass times the gravitational acceleration divided by the G sub C, which is equal to kilogram meter per second squared divided by kilogram meter per Newton second squared. As you can see, the variables with the red one will be cancelled out and will vanish. And then we have the force in Newton will be equal to Newton, which is dimensionally homogeneous. So why do we need a dimensionally homogeneous equation? This is the reason for us to be dimensionally consistent to our working equation. Another one is for us to be not to be confused in what units to be used when dealing multiple components of unit. For us to have an easy way of dealing with our working equation. For example, let's have the energy, which is equal to force times the length it travel. We substitute the formula for force. Energy is equal to Newton meter times mass times the gravitational acceleration times the length. We have the unit of kilogram meter per second squared times meter. We will have the kilogram meter squared per second squared, which is not dimensionally consistent if used in other equations, such as pressure, etc., and will cause confusion in cancelling units. So when we have to make it dimensionally consistent or homogeneous, we have to divide it by G sub C. Then we have Newton per meter, kilogram meter per second squared divided by kilogram meter per Newton second squared, which will be equal to Newton meter, and then will be equal to also Newton meter, which is dimensionally consistent. And there you have it, a dimensionally homogeneous equation. Good luck to everyone.